Hi everyone, and welcome to the very first video in my Automata Theory series. Today we are diving into one of the most fundamental concepts in computer science, the Deterministic Finite Automata, or simply known as DFA. If you've ever found the idea of state machines confusing or abstract, you are not alone. But by the end of this lesson, you'll be able to understand DFAs clearly, trace them, and even build your own DFAs. So grab your notes, stay focused, and let's simplify the automata theory together. Then the outline of what we'll be doing today is, firstly, looking at introducing ourselves into what an automata is, looking at some simple real-life examples of what an automata is, looking at some simple definition of the terms we'll be using in this course, definition of what an automata is, and looking at the types of an automata, which basically we'll be looking at DFAs today in this video. Then in subsequent videos we'll be looking at the non-deterministic finite automata, which are called the NFAs, and also be looking at the non-deterministic finite automata with empty moves, which is also known as the lambda NFA. Introduction to the automata theory. So what is an automata? In my own simple terms, I say automata is the process of getting something done by moving through a predefined path just by me. So I would also say it's the process of converting the control of a machine such that it takes a clicking of a button or probably still the flick of a switch to get the machine working. So that's basically what I would term an automata to be. Just something where you just need it doesn't stress you, just need a click of a button or probably a switch of flick of a switch to get it running. So almost like following a step or steps to having a job done. So examples of what an automata is like is the water tap, whereby it has its initial state and probably it has a state where we would want the tap to be. Let's take for example, we want to get water from the tap, then we take our cup, go towards the tap, we meet the tap at a state whereby it's, let's say there was no water running from it, then we'll say that is the initial state of the tap. And the goal state which we want to get to is when the tap is running with water. So what do? We apply the turn on the head of the tap, then we see water gushing out from the tap. Examples such as disk drives, vending machine, and light switch are also examples of what an automata is. Now looking at the water taps, as we said, we have the initial state, which is where there's no water gushing out. Then when we turn the water tap, we get water getting out, which is our final state in this sense. And when we turn it again from our final state, we get back to the initial state. So if we say from the initial state, how many turns does it take for you to get to the final state? Meaning, how many turns will it take if you're in the initial state? How many turns will it take? Imagine that one turn takes you from initial state to the final state. Therefore, we can say odd number of turns will take you from the initial state to the final state. Let's say we have one turn from the initial state. You can see it takes us to the final state. If we have, let's say, 3 turns from the initial state, you see the first turn takes us to the final state. Second turn brings us back to the initial state, and third turn takes us back to the final state. So we can see there are some turns that would take you to the final state, and there are some equal number of turns that can take you to the initial state. So given this, we can see that if you have 3 turns, it takes us to the final state, which is correct for us. And if we have something like 4 turns or even number of turns, it takes us to the initial state, which is not where we are supposed to get to, which is all wrong. Looking at another example of a real life automata, which is the vending machine, we can see again in this case our symbols are not turns, our symbols are dimes and quarters. So let's say some sequence of dimes and quarters takes us to the final state. We can see the initial state is colored red and the final state is colored green. Therefore, we can say any sequence of dimes and quarters gets us to the final state. And you can hypothetically tell me what sequence can get us to the final state. Just give an example. An example here is taking D from the initial state gets us to the state 10, If we take another D, it gets us to the state 20, and if we take a Q from state 20, it takes us to what? To the final state. So we can see the string DDQ takes us to the final state. You can give another example like saying QDD also takes us to the final state. You can also say Q, then any number of Qs, because it's a loop, because any Q will still bring us back to this state. So this is like a loop which is optional for us. So we can say QDD also takes us to the final state. But there are strings that doesn't take us to the final state. Let's say DD does not take us to the final state. It only brings us to the state 20. And if you say DDQ, it still does not take us to the final state, but it is a valid input in the automata. But it's just it doesn't take us to the final state. So examples like DDQ, as we said earlier, is correct, and examples like or strings like DDDQ isn't correct because it takes us to the state 30 if we start from the initial state, and we might any string that is provided requires for us to always start from the initial state. So from the initial state, if we apply the first D from the initial state, it takes us to state 10. Apply another D from state 10, it takes us to state 20. Another D takes us to state 30, and a Q from state 30 brings us back to state 30, and that is the end of our string. And state 30 is not a final state, meaning it is not correct.
Artlist.io.
Now some simple definition of terms in this series. The first one is an alphabet. What does an alphabet mean? So an alphabet is denoted by the sigma, and it's a finite set of symbols. Just like in our example in previous page, we can see the vending machine has only two symbols, the D and the Q. So when we are told about what is the alphabet of the vending machine we had earlier, we can say it is just D and Q. So all those symbols you can find in an automata are known as the alphabets. If you go back to the tap example again, you can see that the alphabet in our tap example is only ton. So that is the only symbol that can transit. They can give us a transition from one state to another. Now the next is what a string is. So a string is just the collection or a finite collection of these symbols in our alphabet. So if you say DQ, just a combination of D's and the Q's that we had as our alphabet in the vending machine. So this is a correct string. DQ is a correct string under the alphabet's sigma, which is DQ. Now for us to get the length of a string, we just denote that by saying putting S in a modulo sign. And a language is any string that is accepted by an automata. So any string that is accepted means a string that takes us from the initial state to the final state. And in our examples earlier, we can see that 2 tons or 3 tons takes us from the initial state of the tap to the final state of the tap. Even 1 ton takes us from the initial state of the tap to the final state of the tap. So that those strings are known as what? The language. And a unique string of length 0, meaning it does not take any of the symbols, then that is denoted by lambda, and we are going to be looking at that in subsequent videos. And we have something we call this sigma star, which is denoted as the set of all strings over sigma. So any sequence you can think of, let's say going back to our vending machine examples, any sequence we can think of from DQ are all available in sigma star. So even those that are accepted by the automata, those that are not accepted by the automata, in as much it contains DQ. Example D D D D D Q Q Q D Q D Q. This is a value or a string in sigma star.
Artlist.io.
Now looking at the examples, now again going back to the vending machine and the tap, we can see the alphabet in our vending machine previously was DQ, and the sigma star, starting from a lambda, we can have D, which is also correct. If our alphabets are D and Q, we can have D, which is correct, Q, which is correct. We can have DD, DQ, QD. Any sequence or any combination of D and Qs are all in our Sigma star. And you can see in our vending machine that any string U which belongs to the alphabet where U successfully vends. So any string U that successfully vends is our language. And if we go back to the second example, we have our sigma to be turned, because that is the only symbol we have in our tab example. And we have our sigma star to be starting again from empty move to turn. You can see we can have this infinite number of times. So the ones that are accepted, which is our language L, is turn raised to power n, meaning turn raised to power 3, which is turn, takes us back to what the final state. Now, what does an automata mean actually in formal terms? What we've seen earlier is just literal terms. So what do we say an automata is in formal terms? So we say in a formal definition of an automata, or a textbook definition of an automata, is that an automata is defined by 5 tuples, which are: the first one is the Q, which is known as the set of states; the sigma, which is known as the alphabet, as we've seen earlier. We have what we call the transition function, which is denoted by delta. And in this case, in our DFA, since we are looking at DFAs, delta is defined by Q by sigma. We will look at that later on, not to confuse. We have what we call our Q naught, which is known as what the start state, and we have our F, which is known as the set of final states. Therefore, any automata M is defined by these 5 tuples. So types of an automata. Now we are looking at DFA. So we say this particular finite machine requires that every symbol in sigma moves from one state to a specific state only, and that every symbol is accounted for by every state. So in short, you can say that a DFA allows for exactly one transition for each symbol in sigma. So for each symbol in the alphabet from each state. Meaning, if we have a state, let's say, there's an example here. We can see in our example here we have 4 states: Q0, Q1, Q2, and Q3. Now we have the start and we have the final state. In our case here, the start state is the state that has this arrow coming to it. So this is our start state, and our final state are those states that have 2 circles around them. So we have our Q1 and Q2 as our final states, then Q0 as our start state. So a DFA requires that since our alphabets or symbols in an alphabet are 0 and 1, it requires that for every of these states it has an account for 0 and 1. So you can see for Q0, the account for 0 is it comes to Q0, and the account for 1, it is going to Q1. And you can see that 0 is not going to anywhere else apart from a particular place, and also 1 from Q0 is not going to anywhere else apart from Q1. And if you go to Q1, you can see 0 is going to Q2, and nowhere else is 0 going to. Also 1 is going to Q2, and nowhere else is 1 going to. So therefore it has accounted for 0 and 1, and only accounted for them for only one state, meaning 0 is only going to one state and not going to any other state again, and also 1 is only going to one state and not any other state again. Same thing for Q2. 0 is going to Q3 and no other states, and 1 is going to Q2 and no other states. It has accounted for 0 and it has accounted for 1 as well. Going back to Q3 again, 0 is going to Q0 and no other states, and from Q3 0 is transitioning towards Q2 and no other states. So that is exactly what the DFA is. Each of these states must account for the alphabet or the symbols in our alphabet for the automata, and they must account to them for only one state. meaning if I'm accounting for 0, I'm only accounting for it for only one state, and if I'm accounting for 1, that is, which is our symbol here, I'm accounting for it, each state is accounting for it for only one transition. So let's move on. So looking at this, we have the first question here. So according to what we've seen, what a definition of an automata is, or a formal definition of an automata, which we said automata is defined by 5 tuples. So this question arises: what was the automata in the previous state defined by? Now bringing back the automata, you can see, so we can easily bring our definitions from this automata to know what this automata is defined by. Now the first thing in our automata is the Q, which is a set of states, and we can see here we have 4 states: Q0, Q1, Q2 and Q3. So that is that for Q. And we can look at sigma, which is the set of symbols in our alphabet, and we can see in this automata we only have 2 symbols. Again, symbols are just those who are transiting a state to another state, and we have only 2 symbols, which is 0 and 1, and we can see it is equally there. Now the next symbol is our delta. Now delta is a transition function. In this case, we need to draw a table which is transiting us from with our states with our symbols. Now looking at this table, we can see this table comprises of the states, which is initially here, and our symbols, which are up here. So we can transit like this. If I go Q with 0, it takes me to what? Q0. If I take Q0 with 1 in my automata, Q0 with 1 takes me to what? Q1. Now the same thing for Q1. If I go Q1 0, it takes me to Q2. Q1 1, it takes me to what? Q2. Q1 0, meaning Q1 with a 0 transition, takes me to Q2. Q1 1, which means Q1 with a 1 transition, takes me to also what? Q2, which fills up the table. Now Q2 now with a transition of 0 takes me to what? Q3. Q2 with a transition of 1 takes me to what? Q1. You can see it's filled in the table. And for Q3 with a transition of 0 takes me to Q0. With a transition of 1 takes me to what? Q2. Then we can go back to the next thing in the definition is Q0, which means our first state or our start state, and our start state in this case is also what? Q0. Now to our final state. Our final state, again, we have 2 final states in this case, which is Q1 and Q2. Now what I did not prepare here in this slide is to guess a string that is a language in this automata. A language, again, as we said earlier, is just a string that is accepted by the automata, and a string that is accepted by the automata is a string that starts from the final state and ends at the starts from the start state at end and end at its what? Final state. And we can see one of the strings that we can look at is 1. 1 can equally take us from Q0 to Q1, and Q1 is the final state, meaning 1 is a valid language. If I say 0001, it's also a valid language, because 0, which is from Q0 to Q0, another 0 from Q0 to Q0, another 0 from Q0 to Q0, and 1 takes us to Q1. That is also a valid language. And another valid language, let's say 11. 11 is also a valid language, which is 1 takes us from Q0 to Q1. 1 also takes us from Q1 to Q2, which is also a final state. These are all valid, and no valid language is invalid anywhere else, so it's always going to be valid. Now let's see what is an invalid one. You can pause the video and write the string out, probably for 5 seconds, and we'll look at it. So again, I hope you are back. So an invalid one, I guess you've already guessed right, is, let's say, 0 1 0 1 0. That is not accepted. Let's go by it. 0 takes us to Q0 from Q0. Then I'll take 1 from there. It takes me to Q1. Then 0 from there takes me to Q2. Then 1 from Q2 takes me to Q2. Then 0 from Q2 takes me to what? Q3. You can see it is not in the final state. Therefore, this string is not accepted. Now moving on. The same automata. Question number 2. Okay, just as we've done earlier, what is a language for the automata? As we've discussed already, we can see 1 is a language, 001 is a language, 10 is a language, 11111 infinitely is a language. So we can see all these are languages, and you can also pause the video now and see if you can get what is not a language, or if you can get more examples of a language. So question number 2, what is not a language? You can see 100 is not a language because 100 takes me to what? To Q3, state Q3 from state Q0. Starting from Q0, you can see 1 takes me to Q1, 0 takes me to Q2, and from Q2 0 takes me to what? Q3, which is not a final state and is not accepted. Now, in continuation, while drawing the path of a DFA, you notice that it is a straight path for any string provided to be traced. So any string you are provided to be traced by a DFA, it is always going to be a straight path, because as you said earlier, no symbol takes us to two different places. It only takes us to a particular state. So therefore it's going to be a straight path. Looking at this example again, or this automata from previous slides, you can see, given this string 0111001, if we were to draw the path, we can see that it is a straight path. Now starting with the states that are going to be involved. So let's start with Q0. Q0 with a 0 takes us to Q0. Then Q0 with a 1 takes me to what? That is transiting with the second value now, which is 1, takes me to Q1. Q0 transiting with the third value, which is also I'm now in Q1. So Q1 transiting with the third value takes me to what? Q2. Then from Q2, if I transit with the fourth value, it takes me to Q2, which is 1. And then from Q2, if I transit with the other value, the fifth value, it takes me to Q3. As Q0 transiting with a 0 takes me to what? Q3. Then Q3 transiting with the next 0 takes me to what? Q0. And then Q0 transiting with the value 1 takes me to what? Q1. And if you invariably say this string is a language, because it takes me back to what? To a final state. Now more examples of a DFA. Now let's hypothetically say that we were asked to construct a DFA. And again, if I say a DFA, something should just come to your mind, meaning you are going to be constructing automata just like what we've constructed in the earlier slides, but it's just the thing you're supposed to be looking at of a DFA is that every state in the DFA has to have each transition for each symbol. So one transition for each symbol. That is what a DFA is. So you don't need to stress yourself on what a DFA is. Every state you're going to provide in the DFA need to have a transition for each symbols that are given. Now in this case, we're told to construct a DFA that starts with with an A and ends with a what? With a BB. Therefore my symbol is just A and B, and it's also written down here. My sigma is what? A and B. Now how do you go by this? The first thing we need to do is to look at what we're given to transit with. We said the most important things for us to look at is what? A. Then after the A we can have B, starting with an A and a BB. Therefore we are seeing that the most important thing in this is the way I interpret the question. The most important thing is we need to have an A, and we need to have BB, meaning we need to have three things in any string we have. We need to have three things. Then if we need to have three things, then my way of solving this problem is what? We need to have 4 states. Then 4 states we have, starting from Q0, Q1, Q2, then Q3. Then we can now translate the first thing after putting out this these values, we can just pass in the values starting with A, then we end it what with BB. So the first value is starting with an A. That means we are transitioning from Q0 to Q1 with an A, then transitioning from Q1 to Q2 with a B, then Q2 to Q3 with another B. Therefore, we are having a string A. If I give a string ABB now, we can have them. But you know this is not, we can have them and it's going to take us to the final state. But you know this is still not a DFA yet. It is only a DFA if each of these states are accounting for both A and B. And in our case, Q0 is only accounting for A and there is no B from Q0. If you go to Q1, Q1 is only accounting for B and no A. If you go to Q2, Q2 is accounting for B and no A. Then if you go to Q3, Q3 is not even accounting for anything at the moment. Then we need to look at balancing the equation in this time, or in this case. Then you need to carefully, now this is where you need to carefully know how to balance them so that it does not disrupt this beautiful construction you have here. Now the first thing I would say is, let's go back to Q0. So what do we do with B in Q0? Since they said we only can start with an A. Now there are two ways to look at it. Is it that you loop the value that is missing, or you take the value to another state? Let me say, okay, there are three things you can do. It is that you loop the value that is missing, or you take the value to another state, or you take the value to a state called the dead state. Now let's say we loop the value that is missing, a B. Therefore, if we start with any string that starts with B, it is going to be accepted, which is not what we are looking at. Any string that starts with B is not meant to be accepted by this automata. Only strings that start with A is accepted, meaning if I take a B here now as a loop to Q0, therefore if I say B A A B or B A B B, it's going to be accepted because the first B will be looped to Q0, then the next A will be going to Q1, then next B, then the next B, which is also in our final state, and I don't want that. So therefore I cannot loop the B to Q0. Now let's say if I take the B to any of this state, it's still not going to make sense because I can still start with B. It's just, oh, I have a part with A from the first start state, I can also have the part with B from the start state. So that's where we introduce a state called the dead state, where nothing goes there, comes back alive. So the dead state is what we have here. Then we can transit our B to the dead state, meaning this is a state where I don't even want a return, meaning any string that goes to this state does not come back. And in this case, any string that starts with B symbol does not come back at all. It does not come back, which is what we are looking at. A string that starts with A, meaning any string that starts with B is not needed at all. So we are done with the B and the A of Q0. Now going to Q1. Q1 now, we already have an account for B, but we don't have an account for A. So where do we take the A to? Do we loop it? Do we move the A somewhere else, either back or front, or do we take it to a dead state? Now since we've transited the B to D, therefore D can take its A and B to itself, meaning if we have B, A, B, 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 all of it is going to be in the dead state since it has started with what? With a B. So the state D always have the remaining alphabet transiting to itself. Now going to Q1, we already account for B, but we don't have an account for A in Q1. So how do we do that? Again, look at three cases. Is it that we loop the A to Q1 itself, we take the A to either of these states, or we take that A back to what? To D, which is dead state. Now let's look at the first case, looping the A to Q1. Now if we loop the A to Q1, we can have string like A, now any finite sequence of A's, then B's. You can have A, then triple A's, then B, B. If you look at that string, we are having A, B, B. our important thing is that it started with an A and ended with a what? A BB. So we can actually loop our A to Q1 without any problem arising. Now going to Q2. Q2 also has a B but does not have an A. Again, three cases you look at. Either you loop the A to Q2, or you take the A to any of these states, or take it to the dead state. Now let's looking at looping the A to what? To Q2. If we loop the A to Q2, then we can have something like AB going to the final state, which is not correct, because A from Q0 is going to Q1, then B from Q1 is going to Q2. Then if we loop the A to in Q2, then A from Q2 is going to Q2, then B from Q2 is going to Q3. Then we have a string like AB still going to our final state, and which is not supposed to be, because that string is not ending with a what? With a BB. Therefore we cannot loop the A to what? To Q2. What else can we do to the A? Can we take it backward? Now let's take the A one step backward, that is to Q1. Now if we take the A to Q1, we can have a string like A B, which is good, because it's starting with an A and ending with a BB, because this is A, this is B, this is A, and this is B, and this is B, which is correct. So I think taking it back to Q1 is the safest place to go. Then from Q3, what do we do with A and B? Let's start with the A first. Do we loop the A, or do we take it backward? Now let's looking at A. If we loop it with A, therefore we can have strings like A, B, then A, which is not correct. Since we want to end with a B, we cannot loop this place with an A. Therefore, the looping with an A is not correct. Now let's say going back one step with an A. Is it going to be correct? Let's try it. Going one step back with an A, meaning Q3 with transitioning A is going to Q2. Now we can have strings like A, B, then A, then B. Again, that is not correct, because A, B does not is going taking us to the final state, but does not conform with our question, which is supposed to end with a what? With BB. Therefore, this is not also what efficient for us. Therefore, we are not going to take the A backward here. So now let's say we take the A two state backwards. Now we can have something like A, B, then A, then B. Now in this case it is correct. So we transit with our A backwards to that side. So I have my B already out, but I've transited with my A backwards to this side. Then B, I can actually loop it here, because after all, if I've come with A, B, so any amount of B is still going to be what? BB ending. So that is that for that, and I hope you understand. So in this case, we'll be coming to the end of the DFA. I didn't want to make the video this long though, but I hope you understand. I'll be giving some exercises. We are all learning together, as the channel states, learning with Anozi. We are all learning together. So this exercise is the first one is, what is the language of the automata below, and what is it defined by? So we can see this is the automata, and when I say what is defined by, is just those 5 tuples we did earlier on. You name the amount of states you are looking at, the symbols you are looking at, the transition function you can bring out, and the rest. So the start state and the final state. So that's the first question we're looking at. Then the next question is to construct a DFA that can end with what? AB. So our main focus is the DFA should only end with what? With AB. So I hope you can do that. And also the other question is for you to build an automata that accepts all and only those strings that contains what? 001. Now in this case, the automata should only contain what? 001. So in our next video, when we are talking about NFAs, we'll be looking at answers to these exercises. Then looking at answers to these exercises, then continuation of the next type of the automata, which is the NFA. So with this, we come to the end of the video. I hope this helped you build a solid foundation for understanding how DFA works and why they matter to automata. In the next video, as I said earlier, we'll be looking at the NFA, which is the non-deterministic finite automata, and how we can compare them to what, to DFAs. But again, if you find this video helpful, please leave a like, drop your questions in the comments, and subscribe to the channel so that you don't miss whatever comes next. Again, this is my first time recording. You might find some faults in it, but I hope it becomes better in subsequent videos. Thanks for watching. Goodbye.